So today we're going to learn about one-to-one and inverse functions. So by the end of this lesson, you should be able to tell if two functions are inverses, tell if a function is one-to-one, which we'll talk about, find the inverse of a function, and graph the inverse. Now, right away, we need to talk about notation. Unfortunately, in math, sometimes there is notation that's ambiguous, meaning that it could mean more than one thing. When we talk about inverses, we have a notation that can be misleading sometimes. And so if I'm talking about function f, when I talk about the inverse function for f, I'm going to use the notation of f with a little -1 superscript at the top. Just like negative f is wearing a little -1 as a hat. The important thing to realize is that this -1 is not an exponent. It is just a way to designate that we're talking about function f and we're talking about the inverse of function f. So if I were talking about function g, the inverse of function g would be g with a little superscript of -1. We know that we use that kind of notation if I wanted to say 5 to the -1 power, and that would be 1 over 5. But this is not the same thing. We're not talking about that. The basic idea of an inverse is we know functions are mappings. And so here's an example with a function f. It takes these three letter inputs, a, b, and c, and it maps them to a number. A goes to 3, b goes to 1, c goes to 2. Well, it's very useful in mathematics to have the idea of going in the reverse direction. So instead of having my inputs being a, b, and c, now I'm talking about starting at 1, 2, and 3 and going backwards. So from 1, I'm going to go to b, from 2, I'm going to go to c, from 3, I'm going to go to a. So 1b, 2c, 3a. And that is called f inverse because it undoes the function f. It does the exact opposite, the reverse of function f. And it turns out that when we do that, for example, let's call f inverse, let's call it function g. So this will be function g of x. I use a different color. So this will be g of x. Just like you can have more than one name, so can functions. So g of x is the inverse of f of x. So g is f inverse. In this example, g equals f inverse. Well, it turns out that if I take the composition of those two functions, f of g of x and g of f of x, that I'm going to get x for both of those as the answer. And so that is one way that you can tell whether two functions are inverses when you're looking at the equations. So this is true for inverses. So now we know that we can tell whether two functions are inverses by doing the function composition. And here we have a function f of x with a capital F. And we're using this to represent the function where if my input is the degrees Celsius, and I do this mathematical calculation, I multiply it by 9, divide it by 5, and then add 32, I'm going to get the degrees in Fahrenheit. So that's pretty useful for me because if I grew up with Fahrenheit temperature, and if somebody tells me the temperature in Celsius, I don't really have a good feeling for how warm it really is. And so I might want to calculate the Fahrenheit so that I would know whether I need my coat or not. Well, there is a reverse operation, a reverse function, where I could take the input as Fahrenheit, and then my output would be the degrees Celsius, and this is this function, c of x. So my input would be Fahrenheit, and what would come out would be the Celsius. We know from just a minute ago that we can do the function composition, and if I do that and these are truly inverses, my answer for both of them is going to be x. So when I do c of f of x, that's going to be equal to x, and f of c of x is also going to be equal to x. So we're going to verify that. Okay, so let's do the composition C composition f of x. So that means I'm going to take f of x, and I'm going to use the f of x to as my input for the function c of x. So what does c of x tell me to do? It tells me to multiply my input by 5, then subtract 160, and once that is done, then divide by 9. So when I put in x to f of x, the output is 9/5 x plus 32. So that is what is going to go into this x right here. So I'm going to take 9/5 x. So I have 9/5 x plus 32. And I have to multiply that by 5 because that's what the function c does. Takes the input, multiplies it by 5. Then I'm going to subtract 160. And once that's done, then I'm going to divide by 9. So this is the operation. So look at it carefully again and make sure you understand what's happening. So I input x, I find out what f of x is, which is I multiply by 9/5 and add 32. This is my output for f. Then that output is going to go into the x. It's going to become the input for the function c of x. So I'm going to multiply my output for the f by 5, subtract 160, and then divide by 9. So now we just have to do the calculation. So I'm going to multiply by 5, and so that means that we have to distribute this 5. So when I multiply 9 times 5, I'm going to get 45, but then I divide by 5. And so that's going to give me 9. So I have 9x. And then we have 32 times 5. So that's going to be 30 times 5 is 150. And then we have 5 times 2 is 10. So this would be 160. So 9x plus 160. So now we've done the first distribution. The next thing is to subtract 160. So I'm going to minus 160. And then I'm going to divide by 9. And so if we look at the numerator here, we have 9x plus 160 minus 160. Well, that's pretty nice. That's just 9x. And then I am dividing it by 9. And 9 divided by 9 is just going to be x. And that's what we would expect if these functions c and f are inverses. When I do the composition of them, I should get x. There is sometimes some steps that look complicated, but in the end, you should end up with a very simple. It should get simpler and simpler as you proceed in the solution. So doing it only one direction is not enough. It has to be shown that it happens in both directions. So now we're going to do it in the opposite direction. We're going to do f composition c of x. So we're going to take the c of x, which is 5x minus 160, and that is going to be the input into f. So let's go back and think about what f says we're going to do. So we input x, and out came into c, and we got 5x minus 160 divided by 9. Once we have that, it's going to go into f. The function f multiplies that by 9/5, and then once that multiplication is done, it adds 32. So let's see if we can do that. So I'm going to take 9/5 and multiply that by the output for c. So 5x minus 160 divided by 9. And then I'm going to add 32. So what happens here? So the first thing I want you to notice is that I'm going to be multiplying by 9. So that 9 on top is going to cancel with the 9 on the bottom. It's going to divide out. 9 divided by 9 is just going to give me 1. You could do it in steps. You could say 9 times 5 is 45. 45 divided by 9 is 5. 9 times 160 and then divide by 9, and you're going to get 160. So the easiest way is to just think of this as the 9 is dividing out, so that's gone. Well, what happens to the 5? Well, we know when we multiply by a fraction, the numerator gets multiplied through the numerator of the other fraction. This denominator of a fraction is a division. So this 5x minus 160 is going to be divided by 5. The important thing to remember is that it has to be divided into both of these numbers. Just like in the previous problem when we distributed by multiplying, we had to multiply both parts. We have to divide both parts here. So we're going to take and we're going to say 5 divided by 5, that's going to be 1x. And so we have x. And then we have 160 divided by 5. So 5 goes into 160. Well, 16, it goes in there 3 times. That's 15. And then there'll be 10. So this would be 32. So 160 divided by 5 is 32. Why do I have a negative sign here? Because that negative sign was here. So it's the same. And then the last little step is to add 32. And notice now I have minus 32 plus 32, so it's just going to give me x. So both directions we get x as our answer. And so that proves to us that these two functions, f and c, are inverse functions. Now there's an important idea with inverses, and that's the idea of a one-to-one function. Some functions are one-to-one. And those are the functions that have inverses. Some functions are not one-to-one, and those are the functions that do not have inverses. Remember, the inverse of a function is also a function. And so if I have something like this example number 1 here, this is a function that is said is not one-to-one. And if you look at it, the reason it's not one-to-one is I have two inputs, this 4 and the 11, they go to this number 5 for an output. Well, what happens when I go to do the inverse and I start at 5, I don't know whether I should go to 4 or I should go to 11. So this function does not have an inverse. So the idea of one-to-one is that there are no mappings like this where two different inputs would give you the same output. That's okay for a function, but it's not okay for a one-to-one function. A one-to-one function looks like example 2. Every input goes to exactly one output. So then when I go backwards and try to do the inverse, I know exactly where I'm going to go. If I start at 9, I'm going to 2. If I start at 6, I'm going to 4. If I start at 5, I'm going to 11. There's no ambiguity like there is in the first example where if I was doing the inverse and starting at 5, I wouldn't know where to go. So it turns out when you have a graphical representation of a function, there is a really convenient test that tells you whether the function is one-to-one and basically if it has an inverse or not. And it's called the horizontal line test. So you remember, if you think back, to tell whether something was a function, we did a vertical line test, but to tell whether a function has an inverse, we can do something called the horizontal line test. So I'm going to take and draw a horizontal line in this first graph. And if it turns out that if I can draw a horizontal line and it intersects the function more than once, and here you can see that I've intersected this function 1, 2, 3 times, that means that this function is not one-to-one. It does not have an inverse. Two common examples of functions that we've used that do not have inverses are the quadratic functions and also the absolute value functions. And you can see on this quadratic that when I draw that horizontal line, it intersects twice. Now, it is true that I could make it have an inverse if I got rid of half of it. So if I said I was only going to look at x values that were greater than or equal to 0, then I don't have that problem. So you can get around that by restricting your domains. But if we're including the entire domain, No, it does not. It's not one-to-one, and it does not have an inverse. We can see how this relates to the previous mapping. So, I can see here, I know if I put in 2, I get the value of 4. If I put in -2, I also get the value of 4. So when I try and go backwards for the inverse and input 4, well, I don't know whether I should have 2 or -2 as my answer. But if I say, okay, I'm not going to include the negatives, then I do know. And so then you could say, yeah, it has an inverse. And in that case, the inverse would be the square root of x. So here are 2 examples, and we can see that the first one has a horizontal line going through. This is a quartic function. It's a power of 4. Looks a little bit similar to a quadratic, but it's a little flatter on the bottom. And we can see that has the same problem. And in fact, any even power of x would have that problem. This next example is x to the 5th minus 2, and that is a function. There's no spot where I could draw a horizontal line that would touch more than once. Now, it is a little, if you look right down here, it can be a little misleading because it looks like this is flat, but if we expanded this graph and we were able to look at it more closely, we would see that, that you could not draw a horizontal line in there. So this second graph does have an inverse. So how are we going to find an inverse for a function? So there are 4 easy steps. The first step is we take the original equation, we rewrite it without function notation, so that just means changing f of x to y. And then we switch the x and the y, we interchange them. And then once we do that, we solve for y. And then at the final step is we go back to function notation. But since it's the inverse, we're going to use, instead of f of x, it's going to be f inverse of x. So let's do a couple examples. So here's my function, f of x equals 4x minus 3 divided by 5. And this is a linear function, and I want to find the inverse. So to follow our steps, step 1 is to change the f of x to y. So now I have y equals 4x minus 3 over 5. That was step 1. Step 2 says switch the x and the y. So I'm going to use red for step 2. So I'm going to change the x to where the y is, and I'm going to put y where the x is. So I interchanged the x and the y. We switched them. So I use blue for the next step. Now I need to solve this equation for y. So I'm going to multiply both sides by 5. So I have 5x equals 4y minus 3. Then, of course, I'm going to add 3 to both sides. So 5x plus 3 equals 4y. And the last step would be to divide by 4. So I divide by 4. And so my new equation is y equals 5x plus 3 divided by 4. Now I'm still not done because the final step says to take and go back to function notation. So I started out with f of x. So this new function, if I did it correctly, should be f inverse of x. And so I'm going to write that's 5x plus 3 divided by 4. So here's a little graphic that says this graphs of inverse functions, the graphs of a function and its inverse are symmetric with respect to the line y equals x. So that's another way that you can recognize a function as an inverse. Okay, so it's time to look at an application problem. So I will read through it and make sure that you can follow the context, and then we'll highlight a couple things that are relevant. So the first thing is A business property is purchased with a promise to pay off a $60,000 loan plus $16,500 in interest on the loan by making 60 monthly payments of $1,275. The amount of money remaining to be paid on the loan plus the interest is given by this function. F of x is 76,500 subtract 1,275x, where x is the number of monthly payments remaining. So how does this work? Well, we have $60,000 that we owe, plus we're paying the interest fee, which is $16,500. Remember, interest is the money you pay for the privilege of borrowing money. So it's somebody lends you their 60,000, then they're going to get their money back plus some extra money, and that's what that 16,500 is. We're going to make 60 payments. After 60 payments of 1,275, our loan will be paid off. And so I know that 60 times 1,275 would give me 76,500. And you can see the 1,275 in the equation there, because that's monthly payment. Every month I pay, and so X is the number of months that I've paid. So 1 month I would be down 1,275 less that I would owe. 2 months it would be double that, etc. So they're asking us to find the inverse for this function and then use the inverse to determine how many monthly payments would remain. So right now my input is the number of months that I paid, and what comes out is how much money I still owe. So if I'm going to find the inverse, I'm going to reverse that. My input would be how much money I owe, and then based on that, I should be able to calculate how many more payments I have to make. So we're going to look and see how we do that now. All right, so we're going to look at an application where we want to change this into its inverse. And so the 4 steps that you took in your notes are the same we'll use here. Step 1 is to replace the f of x with y. So we have 76,500 minus 1,275x. And the f of x is now y. The second step is to replace the x and the y, or interchange them. So this y is going to go where the x is going to go where the y is. So x is now 76,500 minus 1,275y. Oops. Yeah. And now the next step is to solve this equation for y. Now I don't want to end up dividing by a negative because I'm going to have a fraction. I see this already. So one thing that's allowed is you can do anything to an algebraic solution as long as you do it to both sides. And so I'm going to multiply everything by -1, which is going to change the signs. Alternatively, you can just think you could do an extra step and add 1,275y to both sides. But I'm just going to change the sign. So I'm going to say -x equals 1,275y. So it was negative, it's positive, and the 76,500 was positive, it's now going to be minus. So I multiplied everything by -1. Then the next step is I'm going to add 76,500 to both sides. So I'll have 76,500 minus x equals 1,275y. And the last step is I'm going to divide by 1,275, divide by 1,275. And so my answer is going to be y equals 76,500 minus x divided by 1,275. But again, there is step 4 is we don't want to leave it with a y. We want to go back to the inverse. So it was f of x. Now we're going to talk about f inverse of x. And so this is the final answer, 76,500 minus x divided by 1,275. So this new function is the function where if I input the amount of money that I have left into x, then what's going to come out f inverse of x, the answer is going to be how how many payments I still have left to make, which you might be wondering. Okay, so let's put this inverse function to work. So here it is, the inverse function we came up with, and we owe $35,700 still. So that's going to be my input, and I'm going to subtract it from 76,500, and then I'm going to divide it by 1,275. And so 76,500 minus 35,700 divided by 1,275. And when I calculate this, it turns out that I get 32 as my answer. So that means 32 more payments have to be made. So that's a couple years yet.